So, so let's quickly go through it. So points to be covered today is we will first look into the most important thing. What is the biggest problem when you start a research? The biggest problem, you don't have a problem. That's the biggest problem, right? What's a good problem to work on? So how to choose your problem? We are going to look into do some voting over here as how you choose your problem, and let's see what's your style. Solving the wrong problem, that's a big issue. A lot of times the hardest problem may not be the right problem to solve. So you can be actually tackling a very hard problem, but that may not be meaningful. And I'm talking, this entire talk is about applied sciences, okay? So it doesn't really fit into pure sciences like pure mathematics or humanities or something like that, right? So the scope of this talk is AI, machine learning, and similar such applied sciences. We will also talk a little bit about the no significant contribution problem. How many of you have faced this in your reviews? You get these reviews, and your paper gets rejected, and many times, you get this comment, no significant contribution. So why does that happen? How does that happen? We'll talk about that. And then this is something that I have coined, UBR-driven problem selection. So I'll talk about this. UBR means user behavior research-driven problem selection, and why that's actually a very good way of doing things. After that, I will talk a little bit about the hammer obsession, and this is kind of funny and interesting also. So the problem of not having a problem, right? So how do you choose your problem? So let's have a voting over here. Picking up the hottest topic in town. Who does that? This style of picking up a problem. How many people do this? The first one. They try to pick up the hottest topic, right? In town. Okay. 4 hands. Please be interactive, right? So how many people? First one. Okay. Second one, picking up the less trodden path. The road not taken, sort of. Yeah? Okay. Challenge a supposedly solved problem that everybody is thinking that this is a solved problem, but you have doubts and you are challenging it and you are like a rebel. How many of you are like, is of this character? Okay, great. Picking up a forgotten track. Forgotten, it's not less trodden, it's just forgotten. Okay. Picking up the unsolved, completely unsolved. Okay, great. Create a new problem. Wow. Good. So these are, and everybody is valid, so long as you do this, they are meaningful. So it doesn't matter what is your style of choosing a problem, so long as the problem is meaningful, right? What does that mean? Okay. So the very first thing we need to understand is it even a research problem? And this is where, there is a very thin border line, between research and engineering, right? So a lot of times you choose a problem which is actually an engineering problem, but you think this is a research problem, right? And vice versa. So are you applying a well-researched solution to solve a particular application problem, which is what we technically call problem solving, or is it more of a research? So one way to look into the difference between a research problem and an engineering problem is, what makes this problem really difficult to solve? If that is what you're after, you're actually after a research problem. If that is what your goal is, that I'm trying to figure out what makes this problem really difficult to solve, right? In contrast, if you're trying to put your brain into what makes this solution really difficult to implement, so you have a solution that to scale it up, to make it more robust, to fit into a particular application, you really need to think hard in terms of the design, in terms of the architecture, in terms of how you fit into the infrastructure. That would be engineering, okay? So beware of this thing first. Don't choose something thinking that, okay, this is a research problem, but actually that's an engineering problem. Okay? Many people make that mistake. And when I review all sorts of papers in not just Indicon but a lot of top conferences, I also even in top conferences I also see this issue happening. Who exactly gets benefited? This is the second question, and after you're done with this question, then the second question should be, who exactly gets benefited, or who is the user of your solution? Are you clear on that? This has to be very, very important. I'll show this with an example also. The third question is, how much is the benefit? Let's say you have identified who is the user of your solution. How much is the benefit? How big is the problem the user is facing? I mean, is it a big problem, and you're solving that problem? It's just a small little problem that he or she faces, and you're just solving that. Because if it is a small problem, it's not significant. It can't be considered as an impactful, right? Finally, will that make the user elated, like blown out, or will your solution make him happy, which is not elated but happy, versus it's like, okay, all right, you've done something, but I'm okay. So indifferent. So, and how would you know that? So a lot of times, especially in academic setup, we do not ask these questions actually, and we jump into a problem and we start working on it. Okay, which may lead you to work on actually a problem that nobody cares really. Nobody cares about that problem, and you are solving that problem. Okay, so let's look into this thing. I just sort of animated it a little bit, but anyway. So this is the best paper award of NeurIPS. NeurIPS is going on currently, and this is the best paper award this year. It's the topmost conference in networks and one of the topmost conferences in machine learning. I guess you know it, right? NeurIPS. It used to be called NIPS before. So look at this topic. What is the problem over here? It's marked in red. The problem is back learning of half spaces, right? But then there is a constraint to it, and the constraint is what? Distribution independence. So it has to be solved without having a prior of what is the distribution of that half space, right? And then there's an additional constraint to it. That half space has a particular kind of noise, which is called Mazart noise, right? So that is what this guy is trying to solve. And if you look at the introduction, you'll see this is where, let's say that you're reading this paper, and you're a new researcher, and you want to research into, and let's say that you're interested in back learning of half spaces. So let's say that's your problem, and you're thinking about whether you should go into it, go deep into that. And I intentionally, chose a paper which is theoretical in nature, which is theoretical machine learning. And I will still tell you that why the previous questions are important even for a theoretical paper. So if you look into this section, it says that the problem of learning an unknown half space is as old as the field of machine learning, starting with Rosenblatt's perceptron. You know perceptron, right? So perceptron's algorithm that was in 1958, and has arguably been the most influential problem. So that's what they are starting with, right? This is, you should not even go lower, down. This is where you should ask questions. And these are the three questions that you should definitely ask over here. Now, the first question you should ask is, why is this an influential problem? Is it just because these guys are telling you? No. You need to investigate that. Is it really an influential problem or not, right? Who all benefits if this problem is solved? For theoretical machine learning researchers, it would be, who will be the beneficiaries? People like us who are applied machine learning researchers, right? So what kind of applied machine learning people would actually benefit if this problem is solved? You need to ask that question if you really need to make your research impactful. The third question is the next question to ask. What is the intensity of the benefit? Which means go and ask those applied researchers and talk with them and see whether they really care about this solution or not. Oh, it's done. Okay. So how do you know the progress trajectory? No significant contribution trap. How much of the problem is still open? The big problem with nobody did this before, does that mean you created the problem? Is nobody did this well before? Is that what you're thinking about? What exactly is your research goal? Was it rigidity issue? Does that imply additional proofs? Robust empirical evidences, unbiased experimental design, better evaluation metric? Was it a completeness issue? Is filling the gap a research problem or not? Was it a reproducibility issue? Do you have doubts? So this is how you need to dissect when you walk into a particular problem, right? And that is where what clarifies your research scope. Okay. So UBR-driven problem selection. So that's what I want your attention to. Identify the users of your solution. So if it is theoretical AI/ML, then identify the applied AI/ML researchers who might benefit out of it. Be as precise as possible. That's the first thing. The second thing is see what these users are interested in. Do they really care about the problem you are solving? Ask them how they are solving the problem currently. This is very important before you even think about a solution. How they are solving that problem. How much they are satisfied with the status quo. What would be significant improvement for them? And do not go with this. Do not buy into statements like, let's say you're reading a paper and this paper says, problem X is really important to solve and cites paper B, and paper B says, as can be clearly understood, problem X is very significant, and cites C to Z, and none of the papers from C to Z tells why. And what you did, you just saw this paper and you thought that, well, if this paper is saying important, it means it has to be important, right? Now let's look into the hammer obsession. And I see this so much. I can't just stop myself from talking about it. So hammers, I call it the techniques. The techniques or the approaches. So those are the hammers. So hammers become trendy because of superb marketing. That's the first thing you need to understand. And nothing else. Hammers attract a lot of attention from job market. That's why people are interested in it, for all the wrong reasons. Hammers triggers overinflated or inflated expectation and thereby self-delusion. Hammers can many times seem like the panacea, which means the solution for everything. Example hammers: 1950 to 1985, logic-based symbolic AI, expert systems of 1980s, deep learning of modern times. Right? And this is where I want to warn you. The aftermath of hammer obsession, direct effect of funding. Yes, the winter is coming. Bad press. And the worst thing is, you actually develop an expertise on the hammer. You don't develop an expertise on the problem analysis skill. That doesn't get developed. Tendency towards doing engineering, right? And the worst thing is, other techniques, other AI techniques suddenly stops. It's all in a halt, as if like everybody is following a particular thing, right? This is the new RIPS criteria for paper awards, and look at this. Creativity, unexpectedness, wow. So looks at the problem in a creatively new way, a result that really surprises the reader. This is one of the major criteria for RIPS paper award, right? So you see how important creativity is. meditate on the problem first. So that's, I'm going to very quickly go through it. Meditate on the problem first. Take a lot of time just thinking about the problem. Don't rush into the solution. What is the category of the AI problem? Is it a purely learning problem? Is it an inference problem? Is it a prediction problem? If it is a prediction problem, is it an association analysis problem? Does it require causal analysis, or does it require counterfactual analysis? Most of the time when you see deep learning or all these things, we almost assume that every problem is an association problem, which is not true. So how have researchers described the problem? So these are all the details. I will give you the PPT, you can go through it. Identify what is stopping you to solve, which is what are the hurdles technically, what are the key hurdles, right? So have previous researchers addressed all the key hurdles or not, and so on, right? I'm going a little fast here. So understand the hurdles deeply. Do not think about the solution right now. What is the nature of those hurdles? How researchers have described the hurdles since the beginning? Why the descriptions needed to evolve over time? Are the state-of-the-art descriptions adequate enough? You're just thinking about the hurdles right now, not the solution. What makes the hurdles difficult to overcome? Is it a mathematical difficulty, which means you need certain proofs to proceed? Or is it a computational difficulty, which means you need certain better algorithm to proceed? So finally, the problem should tell you whether you need a hammer or a needle. So this is the crux of it, right? And finally, okay, always remember this. So always remember this part. Okay, questions?
How do you figure out whether the problem is computationally difficult or not? You need to try it. You need to try to solve it using some simple method, right? Is this the right approach?
The right approach would be first to look into how other people have tried to solve it, right? And the very first thing to look into that is, even before the approach, even before looking into how other people have approached it, you should look into this, that what kind of a problem? Is it a rigority issue that are you going after rigority, which means the other works, the previous works were not rigorous enough. And by rigority, what does it mean? Maybe additional proofs are required, or maybe robust empirical, evidences are required, or maybe unbiased experimental design. The previous experimental designs were biased, or maybe better evaluation metric is required, right? Or maybe it's not a rigority issue; it's just a completeness issue, right? So first, you need to look into that, even before thinking about whether the solution was good or bad. That fixes your research goal. Is it a rigority? Is your goal rigority? Is your goal completeness? Is your goal reproducibility? Right? Then after that, what you need to do is you need to, yes, if it is a, let's say, what category of AI problem? I mean, this is something so important that many people miss out on this. What is this category of AI problem? Is it like a purely learning problem, or is it like also involves strategy making and planning? That's the first thing. Not every AI problem is a learning problem. Okay? Is an inference problem, like a deductive inference problem or something, or a statistical inference problem, or is it an inference problem, or is it a prediction problem? So that is something we need to understand, right? So after that, comes the description of the problem. A lot of times you will find when you look into the previous papers that the description itself, the formal description of the problem itself is incomplete. You need to complete the description. A lot of times you will find that the assumptions made by the previous people are not really feasible. They're not valid. They're just for the sake of it. The assumptions has to be questioned, right? So once you modify those assumptions, you have a whole new version of the problem to solve, right? So it's no more a question about the solution. It's a question about the problem formalization itself, right? So After that, if you think that everything is all okay and fine, then you need to figure out how they have described the hurdles. What makes that problem difficult? Intrinsically difficult to solve. What is that property? Whether it is a mathematical property or whether it is a computational property. Maybe there's an intractable issue somewhere. You know, maybe you need a nice approximation algorithm to make it tractable, right? Maybe it's an accuracy issue, right? So why? You know, so you should come to this after you have done all the previous things, not before that, right? So this computational difficulty, whether it is a mathematical difficulty, should only come after you have done all those gone through those previous steps of investigation. Okay? Any other question? Was it helpful? Okay, good. See, as you said, character recognition. So see, so if you go and ask people who are actually engineers who are applying character recognition in different apps, and if you go and ask them, and if you ask them, are you happy with the status quo? And they'll be like, yeah, I'm happy, I'm making business, I'm making money, I'm happy. So then it's just purely academic, and I don't consider that to be, I mean, it's just a little bit of delta here and there, right? So whatever problem you are solving, I would say go with this, start with this things, you know. Go and ask, go and talk with the users first, even before you think about the solution. Talk first, identify who are your users, who are going to be the users, who will use your solution. Let's say you have built the solution, who is going to use it? Do you know? A lot of times you are not even sure who is going to use it. Then go and talk with them. Go and look into what kind of research they do, you know, where they will be applying your thing. And you might very well be shocked to see that they actually don't care, right? So it's just not good enough to just say, and I've seen a lot of papers, you know, even from very good universities, where I don't find this. And that's why you will see that, you know, a lot of these papers are getting dumped, you know, and into a trash can, forgotten after the conference is over, and nobody cares about those papers. Why? Right. So if you really want to make your research meaningful, impactful, if you really want to have that satisfaction within you as a researcher, as a scientist, then this is the way. Go and talk to your users. So you can do all this, any one of these things, you know. You can choose your problem with any one of these, but make sure, this next slide, first of all, make sure of this. This is very important. This is the very first step to do. So after you have, let's say you choose a trendy one, let's say the hottest topic in town, but then you can soon realize that, well, it's not really research, it's actually this. You're actually using some already known solution, and yeah, I mean, I honor this. This is great work, this needs to be done. But let's just be honest about it. You're doing great engineering work. I mean, great engineering work is required. It's nothing lower as such. Right? Any other question before we start? Because we have to